press the bell icon on the YouTube app and never miss another update.
In the previous class, we have discussed about speed of sound in a gas. So, we have discussed Newton's formula for speed of sound in gas, and which comes out to be incorrect because the value of a speed of sound at NTP in air calculated using Newton's formula is found to be 280 meter per second, but the actual value or experimental value of speed of sound in air at NTP is 332 meter per second. Now, Laplace applied a correction to this Newton's formula. According to Laplace, the change in pressure and volume of a gas due to propagation of sound waves in the form of alternate compressions and rarefactions through it do not take place under isothermal condition as assumed by Newton, but it takes place under adiabatic condition, but the temperature does not remain constant. And he has given the corrected Newton's formula, and it is called as a Newton-Laplace formula. So, in the previous class, we have obtained Newton-Laplace formula or Laplace correction to Newton's formula. Now, let us check whether Newton-Laplace formula is a correct formula or not, right? So, now to check Newton-Laplace formula, right. Now, we have Newton-Laplace formula for speed of sound in a gas, that V is equal to square root of gamma into P by rho, where gamma is equal to Cp by Cv, the ratio of two principal specific heats of gas. Cp is specific heat of gas at constant pressure, and Cv is specific heat of gas at constant volume, right. Now, P is pressure and rho is density of the gas, right. Now, for air at NTP, normal temperature and pressure, right. Now, pressure P is equal to 101.3 into 10 raised to the power of 3 Newton per meter squared, or it can also be written as 1.013 into 10 raised to the power of 5. Now, the density is equal to 1.293 kg per meter cube, and we know that the value of gamma depends upon atomicity of gas. It is different for monoatomic, diatomic and triatomic, right. Now, air is a diatomic gas, mainly contains oxygen O2 and nitrogen N2, right. Therefore, gamma value is equal to 7 by 5, or it is equal to 1.4. right? Now substituting in the above equation, substituting in the above equation, we get V is equal to square root of 1.4 into 101.3 into 10 raised to the power of 3 divided by 1.293, and that is also equal to square root of 1.4 into the value of square root of 101.3 into 10 power 3 divided by 1.293, that is square root of p by rho, is right equal to right into 280, or V comes out to be nearly equal to 331.5 meter per second. Right. So we have the theoretical value. V theoretical is equal to 331.5 meter per second, and V experiment is equal to 332 meter per second, right? So there is a very small difference between theoretical value and experimental value. Therefore, so Newton Laplace right formula right is a correct formula which gives a speed of sound in a gas, right? So P is pressure, rho is density, and gamma is right the measure of atomicity, the ratio of right Cp to Cv, right? It is different for right monatomic, diatomic and triatomic gases. So the experimental value comes out to be equal to theoretical value. Therefore, this Newton Laplace formula is a correct formula that gives the speed of sound in a gas. Now, this formula can be applied to any gas like helium, hydrogen, neon, oxygen, right, nitrogen, carbon monoxide, carbon dioxide, sulfur dioxide, etc. Right? But generally, in our day-to-day life, the sound is propagating through air, and air is a mixture of several gases. Therefore, the formula holds good both for gases as well as right air, a mixture of gases. Now let us discuss the factors affecting speed of sound in a gas or in general air, right? So now we will take factors affecting speed of sound in gas or in general in air, we can take it as, right? Now the first one we will take the effect of pressure. Now let us see what is the effect of pressure on gas. Now according to Boyle's law, at constant temperature, right, the volume of given mass of a gas, right, is inversely proportional to its pressure, right. That means V is inversely proportional to pressure, or Vp is equal to constant, right? Now, so from Boyle's law, at constant pressure, so PV is equal to constant, or we can write PV is equal to nRT is equal to constant, right? So where P is pressure, V is volume, right? R is universal gas constant, right? N is equal to, it is mass of gas divided by molecular weight of gas, that is equal to m by capital M, right? E represents the number of moles, right, present in the gas. And also we have, right, density is equal to mass by volume, or volume is equal to mass by density. Now substituting for N and V in this equation, we have P V M by rho is equal to M R T by M. So M get cancel, right? Now that means here P by rho is equal to, right, RT by M is equal to constant. So for given gas, right, M is constant, R is universal constant, and we have taken the temperature is constant. That means to say, when temperature is constant, right, P by rho is, right, a constant. When temperature is constant, so P by rho is a constant, right? Now from Newton Laplace formula, we have V is equal to square root of gamma into P by rho. Here we have gamma is constant, so P by rho, right, is equal to a constant, that is V remains constant. That means to say, there is no change in speed of sound in a gas, right, with the change in pressure, provided the temperature remains constant, right? So the effect of pressure is that so there is no change in, right, speed of sound in a gas with change in pressure, right, provided temperature is constant, provided temperature is constant. It is because we know that, right, density is equal to mass by volume. So when pressure increases, pressure of the gas increases, volume of the gas decreases. When volume of the gas decreases, density of the gas increases. Or that means when pressure increases, correspondingly density increases, right? When pressure decreases, volume increases, density decreases, right? So this P by rho is always remains constant provided the temperature is constant. Therefore, if we go to the higher altitude, actually the atmospheric pressure in air decreases, right, with increase in height. So if we go to sea level or at 1000 feet from sea level, 2000 feet from sea level, 3000 feet from sea level, but the atmospheric pressure varies. Accordingly, density also varies, right? But P by rho always remains constant. When temperature remains the same, speed of sound is independent of change in pressure. Therefore, if you go to sea level or to a hill, the speed of sound remains the same. It is independent of pressure, but provided the temperature remains constant, right? So that is the effect of pressure on speed of sound in a gas. Now, second one, the effect of temperature. The effect of temperature. Now we have speed of sound in a gas according to Newton-Laplace formula. V is equal to square root of gamma into P by rho. Let us take it as equation 1. This expression gives the speed of sound in a gas in terms of pressure and density, right? Now, so from perfect gas equation, now from perfect gas equation, we have PV is equal to nRT, where P is pressure, V is volume, N is number of moles of gas, R is universal gas constant, and T is absolute temperature, where T is absolute temperature, that is the temperature which is measured in Kelvin scale or absolute scale. So its SI unit is Kelvin, right? Now, or this equation can be written as P m by rho is equal to m or T by m. Straight away I am going to this equation, because V volume is equal to m by rho, mass by density, and n is equal to mass of the gas divided by, right, molecular weight. So mm get cancelled, right? That implies that P by rho is equal to RT by m. Let us take it as equation number 2. Now substituting in 1. Substituting equation 2 in equation 1, we get V is equal to square root of gamma. P by rho is shown to be equal to RT by M. Right. RT by M. Right. So this equation 3, this gives speed of sound in terms of temperature and molecular weight, right? So V is equal to square root of gamma into RT by M. So this equation 1 gives speed of sound in terms of pressure and density, and equation 3 gives the speed of sound in terms of absolute temperature of the gas and molecular weight of the gas. Gamma remains the same in both the equation, right? So we have derived speed of sound in terms of temperature and molecular weight. Right. Now we have derived V is equal to square root of gamma into RT by M, where P is absolute temperature and M is molecular weight of gas. R is universal gas constant and gamma is the ratio of specific heat. Now for a given gas, whenever we take any gas, for example air, when we take air, the value of gamma is same, R is same, M is same, right? Now they do not vary with temperature. Therefore, for a given gas, gamma, M, R are constant. In fact, capital R is a universal constant, right? So for given gas, gamma, right, M and R are constant. That means V is directly proportional to square root of, right, absolute temperature. So that is speed of sound is directly proportional to square root of absolute temperature. Suppose what happens if the temperature increases, right? We know that in atmosphere, in a day, right, as time passes, the temperature changes with the season, right, with the time, right, there is a change in temperature of air, right? When temperature of air changes, gamma, M and R value remains same, but what happens, right, velocity or speed of sound in a gas increases with increase in temperature. So speed of sound in a gas increases with increase in temperature. It is a qualitative statement, we can say that, right? Now speed of gas increases with increase in temperature or it decreases with decrease in temperature. Now quantitatively, right, velocity of sound, right, is directly proportional to square root of absolute temperature. That means to say, when temperature is increased by n times, speed of sound increases by root n times. So, suppose when we ask a question, what is the effect of temperature on speed of sound in a gas? Simply we can say that speed of sound in a gas increases with increase in temperature. But the question is asked in a different way. How does speed of sound in a gas vary with temperature? Right? Now we have to say, right, quantitatively how much velocity changes with how much temperature. Suppose when I take the value of n is equal to 4, if the temperature is increased by 4 times, then speed of sound increases by 2 times, right? So, number one, we have taken the effect of pressure. There is no effect of pressure on speed of sound in a gas. Speed of sound in a gas is independent of change in pressure provided the temperature is constant. But the effect of temperature on speed of sound is that qualitatively speed of sound in a gas increases with increase in temperature. Quantitatively, speed of sound in a gas is directly proportional to square root of its absolute temperature, right? Now, with that, let us discuss some formula, right, which gives relation between velocity at 0 degree Celsius, that means at NTP. We know that it is 332 meter per second, and we also know that velocity of sound changes with change in temperature, right? Then we can find the relation between velocity of sound at 0 degree Celsius or NTP and velocity of sound at any temperature T degree Celsius, right? Now we take note point, relation between VO and VT, right? Now what is VO? Right, let VO be speed of sound, right, at 0 degree Celsius or NTP, and VT be speed of sound at temperature T degree Celsius, right? I have taken temperature T degree Celsius, right? Here this temperature at 0 degree Celsius, on Celsius scale it is 0, but temperature on absolute scale is 273 Kelvin, and the temperature T, absolute temperature, corresponding to a temperature in degree Celsius is 273 plus T Kelvin. And we know that speed of sound in a gas is directly proportional to square root of absolute temperature. This is equation 1. Now again, and VO is directly proportional to square root of A naught, that is absolute temperature, right? Equation 2. And VT is directly proportional to square root of temperature. See the difference? So here this is the temperature at 0 degree Celsius. An absolute scale it is 273 Kelvin. This is temperature at T degree Celsius, that is 273 plus T Kelvin. Now let us take it as equation number 3. Now dividing equation 3 by equation 2, we get Vt by V naught is equal to, right, square root of T by T naught, that is equal to square root of T 273 plus T divided by 273, or Vt is equal to V naught into square root of 273 plus T divided by, right, 273, right. Now we know that here the value of V naught, speed of sound at 0 degree Celsius or NTP, is 332 meter per second. By substituting temperature T, we can calculate the speed at any temperature. In fact, at room temperature, around we take 30 degree Celsius, right? The speed of sound is not 332, it is around 350 meter per second, because speed of sound in air increases with increase in temperature, right? So this gives relation between speed of sound, right, at 0 degree Celsius and speed of sound at any temperature, that is in air. When I take this formula, V naught is equal to 332 meter, then it is applicable to air, or this equation holds good for any gas, right, where V naught may not be 332 meter per second, but it is different, right, for different gases, right. Is that clear? Right. Now again, we have this equation, Vt is equal to V naught into square root of 273 plus T divided by 273, or, right, this can be written as Vt is equal to V naught into, right, 1 plus T by 273 whole to the power of half. So 273 divided by 273 is equal to 1. plus t by 273 whole to the power of half. Let us take it as equation 1 here. Now, from binomial theorem, right, using binomial theorem, we have 1 plus x to the power of n is equal to 1 plus nx, right, when, right, x is very small. When the value of x is very small, right, then we can write x 1 plus x to the power of x whole to the power of n is equal to 1 plus nx, right. For small values of t, if the t is very small, then I can write Vt is equal to V naught. Then this expression we have in place of 1, we have 1, in place of x we have t by 273. If t is very small, then t by 273 is also very small, right. Then this can be equal to, that is half into t by 273, or Vt is equal to V naught into 1 plus, right, t by 546, right. This is also the equation which gives the speed of sound, right, in a gas at right any temperature T degree Celsius. So either we can use this equation, or for small change in temperature we can use Vt is equal to V naught into 1 plus t by 546. But here there is a condition that provided t is small, right, but here there is no such condition, right. Right. Now again, continuing our discussion regarding relation between V naught and Ve. So far we have obtained this formula. We have Vt is equal to V naught into 1 plus t by 270 546. Right. Now for air, particularly when we consider air, right, V naught is equal to 332 meter per second. Now usually for all practical purposes we take 332 meter per second. But sometimes we will round off it, right, to make 330. While solving numerical problem, you can use the given value, right. Sometimes they may give 330 meter per second, sometimes they may give 332 meter per second. That depends upon the numerical problem. But if you have not given any specific value, then you need to write, or you need the speed of sound at NTP, then you can use 332 or 330, right. Now, so now we have Vt, therefore, is equal to 332 into 1 plus t by 546, or Vt is equal to 332 plus 332t divided by 546, or Vt is equal to 332 plus, right. Now this 332 divided by 546 is approximately equal to 0.61 into T. Right. So when T is equal to 1 degree Celsius, note down that in any relation, if we use small t, that represents degree Celsius. If we use capital T, that represents absolute temperature in Kelvin, then Vt is equal to 332 plus 0.61, or Vt is equal to 332.61 meter per second at temperature 1 degree Celsius. That means to say, speed of sound in air increases by 0.61 meter per second, for every degree Celsius rise in temperature, from 0 degree Celsius. That means at 1 degree Celsius 332.61, at 2 degree Celsius 332 plus 2 into 0.61. Suppose at T is equal to 10 degree Celsius, then Vt is equal to 332 plus, from this equation, 0.61 into 10, that is 6.1, that is 338.1 meter per second. So at T is equal to 30 degree Celsius, then it is approximately 6.6 into 30, that is 18. So V at 30 degree Celsius is equal to 332 plus approximately 18, that is nearly equal to 350 meter per second, So at 50 degree Celsius, the temperature, speed of sound in air is about 350 meter per second. Remember that speed of sound is directly proportional to absolute temperature of gas or air, and speed of sound increases with increase in temperature of the gas or air. Particularly in air, speed at NTP or 0 degree is 332 meter per second, and speed of sound in air increases by 0.61 meter per second for every degree Celsius rise in temperature above 0 degree Celsius. Is that clear? Now, another point regarding speed of sound. Now we have V is equal to square root of gamma into RT by M. So for given gas, V is directly proportional to absolute temperature. If V1 is speed at temperature T1 Kelvin or T1 degree Celsius, and V2 is speed of sound at temperature T2 Kelvin or T2 degree Celsius. Then we have V1 by V2 is equal to square root of T1 by T2. That means if we know speed of sound in a gas V1 at any temperature T1 Kelvin, then we can calculate velocity or speed of sound in the gas, same gas V2 at any other temperature T2, or this is equal to square root of T1, that is 273 plus T1 divided by T2 is 273 plus T2. So this equation will help us in calculating speed of sound in a gas at various temperatures, right? And again, at constant temperature, at constant temperature, then velocity is proportional to 1 by square root of m. That means speed of sound in a gas is inversely proportional to square root of its molecular weight. That means we take different gases at constant temperature or room temperature, then speed of gas will be different in different gases, because of molecular weight is different for different gases. Which is the lightest gas? Hydrogen. Hydrogen has the least value of molecular weight among all other gases. Therefore, at a given temperature, the speed of sound is the highest in hydrogen gas compared to any other gas. When the molecular weight of gas is increasing, that means we go from a gas of lower molecular weight to higher molecular weight, the speed goes on decreases. At a given temperature, among the gases, the speed of sound is the highest for hydrogen gas, and hydrogen H2 molecular weight is 2 gram, and this which one? Now oxygen O2, it is 32 gram, O 16 gram, and nitrogen N2, it is about 14 gram, Now we will take the third one. Effect of humidity on speed of sound in air. This is also very important. The humidity of air is different at different places on earth, right? Now, so humidity is, or moist air is a measure of water vapor content in air. It is a measure of not water content, it is water vapor content in air. Generally, due to heat obtained by the sun, generally water bodies get heated up and they get evaporated. When they get evaporated, the water vapor get mixed up in air. Generally in our home, when we boil water on stove using a vessel, when the water in the vessel reaches the boiling point, right, then the water vapor can be seen. So how does that water vapor moves? Whether it moves down or moves up? It moves generally upward direction. It's because the density of water vapor is less than density of air. Therefore, it will move in upward direction, right? So moist air or humid air contains water vapor. The most important thing is right here, density of moist air is less than density of dry air, right? So the density of moist air is less than density of dry air. A little bit confusing here. Generally, when we consider moist air, generally we think that so density of moist air should be greater than the density of right dry air, because we know that density of air is about 1.293 kg per meter cube at NTP, and the density of water at ordinary temperature is 1000 kg per meter cube. But moist air does not contain water. It contains water vapor. That's why I have given the example of when we boil water, the water vapor will move upwards. When we fill right a balloon with helium, the balloon will rise vertically upwards, because helium is lighter than air. The density of helium gas is less than the density of air, and that is in accordance with the Archimedes principle, right? Now anyway, but moist air contains not water, it is water vapor, right? So water not in liquid form, water in vapor form, right? So for a given mass, volume of water vapor is much more than the volume of same mass in a liquid state. Therefore, density is very less, right? Suppose when we take a cold drink bottle from refrigerator, right, wipe it with a dry cloth, let it be dry with no water content on its surface. You keep it on a table for 5 more minutes, right? Then when you remove the water, you will observe water, right, at the place of the bottle. Where does the water come? Right? It is because the bottle is very cold, it condenses the water vapor in the air and forms into water droplets, right? Is that clear? Now, so we have V is equal to square root of gamma into P by rho. Therefore, density of dry air, velocity of sound in dry air is equal to gamma into P by density of dry air 1. Velocity of sound or speed of sound in moist air is equal to square root of gamma into P by rho m, equation 2. The presence of water vapor in air does not alter the pressure, right? So, in both the cases, in dry air or humid air, atmospheric pressure is same, gamma is also same. Therefore, we have Vm by Vd is equal to square root of rho d by rho m. Now, density of dry air is greater than density of moist air, or density of moist air is less than density of dry air. Therefore, velocity Vm is greater than Vd. That means, with increasing humidity of air, the speed of sound increases. So, from this equation, it is clear that as the humidity of air increases, the density of air decreases. As the speed is inversely proportional to square root of density of gas. As density decreases, speed increases, or we can say that sound travels faster in humid air than in dry air, right? So, when you go to sea level or beaches, generally humidity will be more, right? Because the ocean water or sea water gets heated up and the vapors enter into the atmosphere, so that the humidity level generally at the sea shores is greater than the other places. Is that clear? Now, so far we have discussed three important, in fact 4 important factors here. One, we have checked out the correctness of Newton's Laplace formula for speed of sound in a gas. It comes out to be a correct equation. And now we have discussed 3 factors affecting speed of sound in gas or air. Number 1, pressure. When temperature remains constant, now speed of sound is independent of change in pressure, right? The change in the value of atmospheric pressure at different places, does not change speed of sound, provided temperature is constant. Now, the effect of temperature. Now, the speed of sound is directly proportional to square root of absolute temperature, or speed of sound in a gas or air increases with increase in temperature. In a given gas, speed of sound is different at different temperatures. And fourth one, particularly in air, humidity or moisture, is concerned, speed of sound increases with increasing humidity. It is because of the fact that in any gas, speed is inversely proportional to square root of density. As humidity increases, density of air decreases, consequently speed increases, right? So, let us conclude at this stage, and in the next class we will discuss one more factor, that is speed of wind, right? How does speed of wind affect the sound propagating through air, right? Anyway, so thank you very much, right? We will meet in the next class.